Okay. Let's see, I'll switch over to the visualizer here in a second. Today we're going to be continuing on with some problems having to do with the power again, so a bit more exposure to that. And then I wanted to introduce something for a lab that we're going to do for our last lab, and it is another measuring the acceleration due to gravity. And in this one we'll be using a pendulum to determine the acceleration due to gravity, and it'll have a couple of new twists in it. So I wanted to talk about that a little bit. So let's switch over. This has a bunch of stuff from the previous class on it right now, so don't panic when you see that. Special relativity is the topic of that material, but our things are, actually, where'd they go? Here they are. Let's see. I think I'll talk about the lab first, and then we'll get into some more power thing. And so this will be finding G with a pendulum is what it is. And I'll start off with a little sketch. Whoops, ing, finding little g with a pendulum. And we start off with, you can imagine that you've got a pendulum, which is just going to be a long string with a little brass sphere at the end of it. And we just let it swing back and forth. And the expression we're going to be using is an approximation, but it works pretty well as long as you keep the pendulum angle small. And when we actually do the experiment, I would encourage you to keep the angle less than about just a few degrees. So to actually make it swing, you'll just have the pendulum down here at the bottom, and you'll just move it to the side just a few inches and let it swing. And then that'll keep the angle small, and it'll swing for a long time that way. Through math, that is beyond the scope of this course, but understandable for people who've had second quarter calculus maybe, or even first quarter calculus. There is an approximation that has to be made, but you can find out that the period of a pendulum ends up equaling 2 pi times the square root of the length of the pendulum divided by the acceleration due to gravity. And so if you were doing this experiment on the moon, you'd get different periods for the pendulum that you happen to have. In fact, that's one of the questions that I ask at the tail end of the lab, is how that happens to work out. And this is probably the first example of periodic motion that people ever studied. And that's motion that just keeps repeating. And it's actually, if you keep the angle small, this formula is a very good approximation of how things work out. And the period ends up depending only on the length of the pendulum, as long as you stay on Earth, so that you don't have to worry about G. Well, in the experiment, what we do is we vary the length of the pendulum, go through a whole series of length increases, and then we're going to make a graph. Now, if I graph T versus this expression as it is written right now, I'd have the 2 pi over the square root of G here, and then I'd have a square root of L. And when you graph something versus the square root of something else, we're not going to get a straight line. And so we wouldn't be able to figure out G from that. But if you just square both sides of this thing, and this is a trick you can pull once in a while, well, you'd square the 2 pi and you'd get 4 pi squared, and then you'd have L over G. And the actual variable we have, the independent variable, the thing we can change, is L. And we're seeing how T squared depends on that. But if we go ahead and do the analysis on that, or just a little bit of algebra rearranging here, all of our measurements are done on Earth, so we're going to have the same value of G here. This quantity in parentheses here ends up being the slope of the graph. So we can measure L, we can measure T with a stopwatch, and so this is a way of figuring out the acceleration due to gravity. And when we make the graph of this, we're going to have T squared on the vertical axis, and that'll be in seconds squared. And then we'll have L on the horizontal axis, and centimeters would work just fine for this. And we'll get this series of data points. I think we have close to 10 on this lab. And if you draw a straight line that best approximates them, the slope is going to equal this quantity in parentheses here. So the slope will equal 4 pi squared divided by G. Now the slope's going to have units of rise over run, like slopes always do, but the rise is measured in seconds squared and the run is measured in centimeters. So it's seconds squared over centimeters would be the units of the slope. And that's going to be kind of a weird thing, but you can deal with it. It's just algebra at that point. But then you take the number you get for the slope, and let's just call that number B that you happen to get, and you just set B equal to 4 pi squared over G, and then solve for G. Multiply both sides by G, and you'd get BG equals 4 pi squared, and G is going to equal 4 pi squared over the slope. And so that's how we will find the acceleration due to gravity in that experiment. And turns out if we had a course where we were meeting frequently, we've got a couple of different labs where we end up with an expression start off with an expression that looks something like this. For instance, a mass that's bobbing up and down on a spring does something very much like it, except in that case, instead of L over G, we would have the amount of mass on the spring divided by the spring constant. So it's a way of finding the spring constant as well, something very similar to this. So those are things that happen. But this is just another way of determining the acceleration due to gravity. And I'll do what I did with the Atwood's machine lab, and that is to gather the data and provide you with that, and then you make the graph and go on from there, answer some questions in there. So, and I'll be posting that soon. Let's see, other things. I have gone through I'm nearly done with the test 1 redos that you did as far as grading those. And some of you have pretty well maxed out the possible points on there. Some of you, and I'm speaking to the greater class here, but some of you still didn't have the correct idea on some of those questions, but they're things that we can address during our review for the final. In fact, I think a good thing to do with that would be to go through the test that you just took last week, and then that first test, just go through those and see how to do every one of those questions. And that would help you out, I think, to see that, especially now that you've actually wrestled with those questions a bit. So I'll be mailing those out soon. What I'm going to do is, I haven't actually written anything on the test redo you did, but I wrote down the new scores that I gave you on the questions in an Excel file, so I could just immediately do the calculations in Excel to figure out your new scores. And I'm gonna just use the snip tool and snip you the part out of the Excel spreadsheet so you can see what you got on that redo anyway. And that'll be part of the emails that I'm sending out to you. But I still have a couple people's to get through. So there's that. Now, yesterday we were doing power, and did a few examples with that. And then there's a couple of conservation of energy questions that I wanted to address, and we'll see how that happens to work. Let's see. There's that one. Yeah, we've got quite a few here that are sort of interesting. All right, this one. These, I think most of these are straight out of your book. So what's the average useful power output of a person who does 6 times 10 to the 6 joules of useful work? That's 6 million joules of useful work in 8 hours. So working at this rate, how long would it take this person to lift 2,000 kilograms of bricks, 1.50 meters to a platform? And all right, so anyway, 6 million joules in 8 hours. Well, I think since our power ends up being the amount of work done divided by the time, we can write the work there, 6.00 times 10 to the 6th joules. And then on the bottom here, I'm going to have written into it a unit conversion problem. We're given 8.00 hours, but those aren't our usual unit of time that we need. We need joules per second, but actually I could just multiply this by 1 hour over 3,600 seconds. Okay, and that would get rid of the hours, and in the bottom I would just have 8 times 3,600. So that's just a matter of plugging it into your calculator. I do have to wrap my bottom and denominator there, wrap the denominator in parentheses there. Ugh. Good thing it's the last day of the week. And this was only a 3-day week. 8 times 3,600. And I would get about 200, we have 3 sig figs on both of these, joules per second, which are watts. And I almost wrote the work as just a plain old W here, but that would have gotten confused with our unit of power over here, a watt. So I wrote out the word for work. So that's part A of that thing. And then working at that rate, how long will it take to lift 2,000 kilograms of bricks, 1.50 meters to a platform? Well, let's figure out how much work actually has to be done to lift those things 1.50 meters. And the work in that case, you're working against the force of gravity. It's going to be the force you have to exert, which is the weight of 2,000 kilograms of bricks, times, well, that's just their mass. I have to multiply that by 9.81 meters per second squared to get the weight of them. So there's a force times the distance that you have to lift them, 1.50 meters. So here's the force, here's the distance. Work is equal to force times distance. So Now, you're going to be lifting not the whole 2,000 kilograms at a time, but you might be lifting 10 kilograms at a time and then doing 10 more kilograms at a time, and you would just add all of those together, but you'd end up with the same expression here. So we can calculate that total amount of work. And I get about, let's see, we don't have a very precise, or we don't know how many sig figs this is, but I'm just going to call it 30,000 joules of work. Newton meter is a joule, so that's what we have. Now, our power rate is 208 watts, and that's work over time. And so we have 208 watts, if we're still working at the same rate, is going to equal 30,000 joules divided by some time that we don't know. And I'm just going to call that time delta T. This would be a work divided by time, and we want to have this rate of work be the same as the rate of work that they did up here. So the thing I don't know is delta T. So multiply both sides by delta T, and I'll get 208 watts times delta T is equal to 30,000 joules. So it helps to keep thinking of work over time as being what power happens to be. And if you've got that locked in, now I divide both sides by 208. So delta T will equal 30,000 joules divided by 208. Now I'm going to rewrite that watt as a joule per second. And unit-wise, I've got joules on top. I'm dividing by joules per second, but when you divide by a fraction, you invert and multiply. I get seconds over joules. The joules divide out, and I'll end up with seconds here. So just want to convince myself of that. And I still have this number more or less stored in my calculator. I've got an approximation of it, and I'm going to round off whatever I get to, whoops, one significant figure, I think. Oh, let's see. Oh, it's not that long. It's only about, this person might be tired. I get about 140. Now that's keeping two significant figures, so that's pushing things a little, but only about 140 seconds. Let me check that. Oops. I should know better than using different fingers. Yeah, it is about the same. So only about 140 seconds. That's going to be 2,000 kilograms is a lot of bricks. Was that 208 correct? I'm going to check that out. Yeah, it was. It was 6 million divided by 8 times 3,600. This seems a little unbelievable, but maybe this person's kind of impressive anyway. 2,000 kilograms of bricks would weigh about 4,400 pounds. And I don't even want to think about having to move those things onto a meter and a half onto a platform, but you'd have to work pretty fast, I guess, to do that. Okay. this is the energy chapter, and there's some interesting questions in here. We're going to need scratch paper for this. Calculate the power per square meter reaching Earth's upper atmosphere from the sun. And the power output of the sun is rounded here. It's actually, I think it's 3.86 if I remember, but this is close enough. That many watts, 4 times 10 to the 26 watts. Something we do in my astronomy classes, at least spring quarter. It never seemed to work fall quarter, but usually in the astronomy classes, when we get to studying the sun in person, by the time we were doing that in the quarter, we were into May, and it's usually nice out just about every day. So we'd walk outside and I'd have the students hold their hand out to the sunlight and just try to remember how warm their hand feels when they're doing that. And then we'd go back inside, and inside I'd have a 100-watt light bulb, and it's the old incandescent type of light bulbs that put out mostly heat, it turns out. Most of that 100 watts goes into heat. But I'd have people move their hands closer or farther away from the light bulb until they felt the same amount of warmth that they had when they were outside holding their hand near in the sunlight. And then turns out that the power or the intensity of light that you're getting is what your hand is sensing, and it depends on 1 divided by the square of the distance. And so we can measure the distance from their hands to the light bulb, and we know the distance to the sun, and it turns out that the power output of the sun divided by the distance to the sun squared would equal the 100 watts of the light bulb divided by the distance to the light bulb squared. Okay, well, we know the distance to the sun. It's 93 million miles or 150 million kilometers, and so we could express that in just meters. The distance to the light bulb would usually end up being something like 8 centimeters or something like that, which is 0.08 meters. And with that, we'd come up for an estimate of the power output of the sun. And we'd usually not have a lot of significant figures, but we would get the times 10 to the 26th part correct. And usually we'd be somewhere between about 2 and 5 times 10 to the 26 watts. And so we weren't exact, but still, considering how crude our instruments of measurement were, we were just trying to remember when the light bulb light seemed to make our hand feel the same way it had out in the outside, exposing it to the sun. But anyway, part of it's absorbed and reflected by the atmosphere, and the maximum that reaches the Earth's surface is about 1.30 kilowatts per meter squared. Now, kilo just means 1,000, so this would be 1.30 thousand watts per square meter, or 1,300 watts per square meter. And calculate the area in kilometers squared of solar energy collectors needed to replace an electric power plant that generates 750 megawatts, woof, if the collectors convert at an average of 2% of the maximum power into electricity. And that small conversion efficiency is due to the efficiency of the devices themselves. I remember hearing a talk by someone from REC, that's the Renewable Energy Corporation that manufactures silicon for solar cells in Moses Lake, and they're not manufacturing right now because of some tariffs that China is imposing on silicon manufactured at other places. But they're hoping to start up again, I think next year, manufacturing silicon out there. But I think their efficiencies were higher than 2%. I thought they were getting up close to 10%. So that would be good. For a long time, the problem with solar energy was that it was more expensive, quite a bit more expensive than things like coal-fired power plants or other means of generating electricity. And part of the reason for that was that they weren't very efficient, but now they're getting much more efficient. But this is a multi-part problem. First, we want the power to be 750 megawatts. So then I'll worry about converting the mega into something there. And somehow we're going to have to get that from solar energy. Well, we're going to have to take this number, 1.30 kilowatts per square meter, and multiply it by some area of solar collectors. So 1.30 kilowatts per square meter. And then we have to multiply that by a bunch of solar collectors, except that those solar collectors are only 2.00% efficient. And this is a situation where if I multiply this is the power delivered per unit area by the sun at our orbital location. If I multiply that by an area, then I'll get an amount of power that is being delivered by the sun, and I'd like it to be that, except the things that I'm using are not 100% efficient. If they were 100% efficient, 100% efficient, I could just use this as it is, but I have to multiply it by 0.0200 in order to make that thing correct. And so basically I had to develop this equation on my own, knowing the total power output I wanted and knowing the power per unit area delivered by the sun, and then having to do something like this. So we can figure out what the area is going to be. And if I solve for the area, it's going to be my 750. Now I'm going to replace that mega with times 10 to the 6th watts. And I'll divide by my 1.30. That's a kilowatt. So that's times 10 to the 3rd. And this is watts per square meter. And I also need to have this 0.0200 in here. And notice that this is a pure number, but or something without dimensions. Notice it's on the bottom of the fraction. And because I'm dividing by something less than 1, it's going to make my final number bigger. And because those solar collectors are only 2% efficient, the area needed to provide the needed power here ends up being much larger. But we can multiply into here or do the math and see what we get. And this is just trying to figure out one of these things. So whoops, clear. I don't know where I am. There we are, clear, okay. 750 times 10 to the 6th divided by, whoops, I'm gonna wrap the numerator or the denominator in parentheses. That's just 1300 is what it is. So rather than having to use scientific notation, but I'm going to multiply by 0.0200. I'll figure out the area. This is was there anything that I didn't have that much precision on? Oh, this only has 2 sig figs. So I'm only going to keep 2 sig figs. That 0, you don't know if it's significant or not. But this looks like 2.9 times 10 to the 7th. Now, unit-wise, I've got watts divided by watt per meter squared. Flip this thing on the bottom and multiply, and I'd have meters squared over watts. This will be meters squared, is what it happens to be. And, oh, we want an area in kilometers squared. Okay, so if I multiply that by 1 kilometer divided by 1,000 meters and square that, then I'll have kilometers squared. So I'm going to divide this by 1,000 is 10 to the 3rd. 10 to the 3rd squared is 10 to the 6th. I'll get 2.9 times 10 to the 1st, I think. But I'll go ahead and divide it by 1,000 squared. But I think I'll get 29 square kilometers. Yes, I do. So that's quite a bit. Now, if instead of only being 2% efficient, if your solar cells are 10% efficient, that's 5 times as efficient. You'd only need 1/5 of this area, so 5 kilometers squared. And I want to think that I heard they were even more than that, but I don't remember for sure what the value was. It was in a talk I heard from a guy, oh boy, maybe 6 or 7 years ago. I'm not sure. Okay, but with the same assumptions, what area would be needed to meet the annual energy needs of the top 5 energy consumers in the world? And we'll look at the table below. Let's just do it for the US and see if we can figure it out. Now, this is the number of joules used per year. And so to get an actual power on there, we're going to have to divide that amount of energy by the number of seconds in a year. And I don't remember if you remember this from, or don't know if you remember this from yesterday before, but 1 year is equal to about 3.16 times 10 to the 7th seconds. And I'm pretty sure it was yesterday that we did that. So in the US, our power usage is going to be 9.49 times 10 to the 19th joules. I wonder if that's the way it was expressed in your book or not. Not sure. But we can figure out the power usage and then just do this equation again. So okay, now in this case, we can actually keep 3 significant figures in our results. So we'll have 3.00 times 10 to the 12th watts. So 10 to the 6th is megawatt. 10 to the 9th is gigabyte, and 10 to the 12th is terabyte, or not terabytes, tera. I'm thinking of computer memory. So this would be 3.00 terawatts is actually what the units happen to be. Not that we need to know that, but we can figure out the the area that we're going to need. And it's probably going to be a big area. So it'll be 3.00 times 10 to the 12th watts are going to equal, I'm going to write this as 1,300 watts per square meter again. Times A times 0.0200, because they're not perfectly efficient. And so the area in this case, oh boy, is going to be big in square meters especially. So okay, and we'll be down to 2 significant figures because this only has 2. No, it actually had 3, so we can keep 3 sig figs. And again, the units will come out square meters, which we might leave that way, but we'll see. Divided by and I get about 1.16 times 10 to the 11th meters squared. But again, if I multiply that by 1 kilometer over 10 to the 3rd meters and square that, I'll be dividing by 10 to the 6th. And so I'll get an area of 1.16 times 10 to the 5th kilometers squared. Now, if you imagine that that is a square, like the state of Colorado, it's not perfectly a square, I think it's a rectangle. But anyway, that has that area would equal the length squared. So if I take the square root of that, it'll tell me the area of a square piece of land that might work for. So first I have to divide that by 1 times 10 to the 6th, and then take the square root of that. And it would be 340 kilometers on a side, and that's good to 3 sig figs. And if I multiply that by 1 mile over 1.61 kilometers, it'd be a square of land 211 miles on a side, which is a pretty big chunk of land. That would completely cover some of the smaller states in the US. They'd be blanketed with solar panels. But I wouldn't be surprised, well, actually, that area would shrink quite a bit if you've got solar panels that are more than 100% efficient. And I've read about people who are trying to figure out materials for building roads out of that could be solar collectors. That might be a possible way that you could do it. I'd be willing to bet that we have that many square miles that are covered with asphalt in the United States right now. So anyway, that's kind of an off-the-wall question. I would not hit you with one like this on a test, but just gives you some idea of what you can do when you start thinking about some of these power and energy relationships. We can do this problem now. This is an example of something. It's a a work and energy conservation thing, but it's one where we actually have a coefficient of kinetic friction. And when this is the case, you'll lose energy, but we can calculate what to do with that lost energy, or how much that lost energy will be, and see how this might work. And the idea is that we'll start off with some amount of gravitational potential energy. And I know sometimes I use a U to stand for that, and sometimes I use this GPE. We'll have that. We can start off with some initial kinetic energy. And if there was no friction, we would have the gravitational potential energy final, which I'm going to define this to be 0 down here, so that'll be 0, but plus the kinetic energy final. Okay. And if there was no friction, these two would equal each other. But because there is friction, something I add to this is the work done by friction. Now, that work is going to be negative. The displacement is down the hill or down the plane. The frictional force is in the opposite direction. And so there's a 180-degree angle between the direction of the frictional force and the direction of the displacement. And that'll make the work done by friction be negative. And so we'll have that to consider here. But this is a way that I could set this up. And if I say, let's see, delta x, they give me that that's equal to 3.79 meters. The angle theta is 37.6 meters. And so something I can do is figure out the height, this height h here, h over delta x. That's the side opposite the angle divided by the hypotenuse. That's going to be the sine of that angle theta. And so I can figure out the height that it descends through. It's just going to be delta x sine theta. And I'm just going to plug in the numbers and calculate it out here. It's 3.79 meters times the sine of 37.6 degrees. Those two look a lot alike. And I get 2.31 meters. So that's what that is. And so that initial gravitational potential energy is going to be mgh, because I'm going to decide that GPE is equal to 0 down here at the bottom of the plane. So that's something that I have, which means this is going to be 0. Okay. Now, in this case, you give it a shove down the plane so that the initial velocity is 5.43 meters per second. Okay. So that's not 0 as it might be if we had a frictionless situation, but V initial is the 5.43 meters per second. So that initial kinetic energy is going to be m times, 1/2 times m times V initial squared. That's supposed to be a 1. Anyway, that's what kinetic energy always is. Okay, the final kinetic energy is 1/2 m V final squared. And I don't know what V final happens to be. Notice nowhere do they give me the mass of the block, but so far everything I've got is proportional to the mass. The thing that I haven't figured out is the work done by friction. All right, well, here's things I know about friction. The frictional force is going to equal mu sub k. It's sliding, and it's the coefficient of kinetic friction that they give me. It's going to be mu sub k times the normal force. But the normal force isn't going to be the weight because it's on an inclined plane. So I'll have to do something to do with that. And the work that's done by friction, it's going to have a minus sign because the frictional force is up the plane and the displacement is down, but it's going to equal that frictional force, mu sub k, times n times delta x. And I know delta x, I'm given that. It's here. The only thing I don't know is the normal force. And I'm going to do that off to the side on a piece of paper here to try and understand this thing. But here's what I'm going to have for forces. I don't usually draw a solid line on a free body diagram, but I will have mg acting downward. The normal force always acts perpendicular to the surface, and so that's the normal force. And then this plane is inclined at an angle theta. There's one more force acting here, and that's the frictional force. And so I'll have the force of friction up there. Whoops, I called it capital F and lowercase f, so I'll do that again here. But that's up the plane. Now, all the action takes place up and down the plane, and there's probably going to be acceleration here. I would expect it, although not necessarily. Actually, I would expect it to accelerate because it's a really slick plane. The coefficient is 0.072. That's a small coefficient of friction. But I don't care about what's going on in the up-down direction anyway, because all I want is the normal force, and it will equal the component of the weight that is into the plane. And the reason it's equal is because in this situation, you're not going to see the mass falling through the plane, and you're not going to see it jumping off the plane. It moves down the plane, parallel to the surface. With a bit of work, you can figure out that this angle is going to be theta. And actually, here's how I do it. In a right triangle, if this angle is theta, this angle is 90 minus theta. And then this angle here is another right angle. So if this one is 90 minus theta, a right angle is a 90-degree angle, this one has to be theta because this angle plus this one have to add to 90 degrees. So this is theta. The component of the weight that is into the plane ends up being mg cos theta. And the component that's down the plane ends up being mg sine theta. We've done a few problems like this before. Sorry that I wrote those really tiny, but in this direction, the forces are balanced, so the normal force has to equal mg cosine theta. And I go through that every time because if you're faced with a situation like this, you want to have seen it, and you should try it out on your own to convince yourself. So anyway, the normal force is mg cosine theta. The work, or the frictional force, is mu sub k mg cosine theta. And the work done by friction is going to equal minus mu sub k mg cosine theta times delta x. So my expression up here, the only thing that was missing was this part to do in there. So now I can write mgh plus 1/2 mv initial squared. This is the energy that I start with. This next term is the energy I'm going to lose because friction does work on the block. So that's what I end up And that'll end up being the energy that I finish with, the final squared. Sorry, that's a little crowded, but energy I start with minus the energy I lose equals the energy I end up with. And this is a conservation of energy problem. And notice every term in here has the mass, which is why they didn't bother to tell us what the mass was. So I can divide that out. Let's see, 1/2, whoops, the initial squared, I forgot the GH, plus, that's a G, minus mu sub K G cos theta times delta X, lots of stuff to plug into your calculator on this one, is going to equal 1/2 V final squared, or I need to, if I multiply both sides by 1/2, on this right side I'll have just V final squared, and multiply everything by 2 and I'll get 2GH plus V initial squared minus 2 mu sub K G cosine theta times delta X. And this is a lot. Anyway, that'll be 2 times 9.81 meters per second squared times the height that we figured out here way back long ago. That was 2.31 meters. Plus that initial velocity was 5.43 meters per second. And that's squared minus 2 times mu sub K, which is 0.072, times G, which is 9.81 meters per second squared, times the cosine of 37.6 degrees, a million things to put into your calculator, times delta X. I ran out of room. Delta X is the 3.79 meters. And then that's all equal to V final squared. Okay, we're a bit over time, but you can finish off that multiplication. You'll get meters squared per second squared when you do that, and you need to add all the numbers together and then take the square root, and you would have V final. But this is a situation where you start off with some initial energy and friction steals some of that initial energy, so you're going to have less at the end than you started with. So that's the way you do that thing anyway. Okay, any questions on that one? I know it had a lot of stuff in it, but at any rate, be watching for the graded test 1 redos, and then a new lab assignment as well. And so they'll be arriving here probably this afternoon, I think. So we'll go from there. Okay. Otherwise, have a good weekend.